welcome back to our latest lecture session. So we have been looking into applying our component balance and also looking at how to at the same time apply VMINTEQ, right, to be able to solve our acid and base related equilibrium questions, right. So acid and base, that's what we are going to look at again, right, because that's going to be a fundamental aspect for environmental engineers. And again, why is that? Because pH is a master variable, you know. Wherever or whichever aspect you look at, rarely will you find a system where pH is not worthwhile, or you know, pH is not important, let's say. Especially if it's inorganics, pH is certainly going to be important because you need to look at the charge, right? Even the same case with organics, but not to a great extent. But we are going to come back to that later on. So again, we have been looking at issues with respect to, I believe we started out looking at, I have one particular acid and a particular solution, what's the pH and equilibrium solutions. The second, I think we looked at how a sodium acetate or the relevant conjugate base and what's going to the pH and the relevant equilibrium concentrations. Next, I believe we looked at two mixtures, right, or two solutions, pardon me, and we looked at what's it going to be, or what is it as in the equilibrium concentrations, right, what are they going to be for this mixture. And more we are shifting towards equilibrium, but we always need to have a basic understanding about the fundamental process. So that's why we are still trying to have an understanding about how to solve that by hand. And how do we do that? By looking at conservative quantities. And what are these conservative quantities again, please? These are the components that we are defining, right? So in this class, we are going to look at an inverse problem. So for example, let's say I ask a student what do we say, this is the solution, right? And I want you to bring down the pH to a particular value, let's say, right, let's say 3 or 4, let's say, and this is the only acid that I have in my lab, and let's say I don't have enough solution, so you can't do trial and error to get it out, or you know, to try it out, let's say. For example, she can take 10 ml, add the relevant volume, look at it proportionately and so on. So let's say she or he doesn't have that particular flexibility because the volume of sample is less. So what can you do? I guess looking at, not guess, you can making some approximations with respect to the species present or the compounds present in that particular solution, use VMINTEQ to be able to relatively, I guess, relatively, you know, come up with a precise answer. Relative, I guess, so it's because you don't know or you don't have complete information about your particular system. You are going to make assumptions that certain compounds are present or absent and so on. So in this case, we are going to start looking at today's session. We will start out looking at an inverse problem, right? So until now, what do we look at? I put in HAC or you know, acetic acid. What's the pH that I can expect and what are the equilibrium conditions? But here, what am I asking now? For a pH to be a particular value, how much HAC do I need to put in? So that's what we are going to look at, right? So here we are going to look at the inverse problems, number 5, I guess, the inverse problems, right? So the setup, again, the components, component balance and everything is going to be the same, but let's try to understand the system now. So let's say, let's take the example with respect to the pH is supposed to be 3. We will see why we chose 3, okay. So I want pH to be 3 and I want to know how much of HAC do I need to put in, right, initially to be able to get to a pH of 3, right. What is the concentration of HAC that needs to be added initially, right. So how do we go about this now, right. So again, it might seem relatively more complex, but it's just issue of identifying the knowns and the unknowns. So earlier we did not have the concentrations of the relevant variables at equilibrium, but we had the concentrations of the recipe species or whatever it is that we are adding initially, right. We had this or the initial concentrations, but we did not have the equilibrium concentrations. But now we have the equilibrium concentration, if not concentrations. Why is that? Because I know that the pH, at least one of these variables, which is H plus, the pH is 3. I know one particular variable, but I did not know the initial or the initial variable, right, and that is HAC naught. So I am going to play around with this and we can solve it accordingly. So it's going to be more or less the same case, right. You are going to use what do we say, define the same species, right. What are the species? Those at equilibrium, you know, HAC, AC minus, H plus and OH minus, right, and components are going to be what now? H plus and AC minus. And how do you choose these components now? You choose them by saying that or looking at the proton always H plus, and then choosing the most deprotonated form, which is the acetate ion in this particular case, most deprotonated form, right. Again, component balance, I am skipping the formation equations, and we have these HAC, AC minus, H plus and OH minus. So, we will see that more or less the key is H plus, just H plus balance. So, 1 0 1 minus 1 1 1 0 0, and if the recipe species are HAC naught, which is my unknown, right. This is my unknown now, right. And what do I have here? That is going to be equal to my unknown. So, I am going to leave it as it is. So, I am going to do the balance on H plus. So, an aspect that you need to consider is why are we doing the balance on H plus or H total and not your acetate total. Why is that? Because if you look at the H total, and which we are going to look at obviously, I guess, the equation, you can see that it is easier for you to transform it into an equation with just a single variable that we already have information about. What is that? The pH, right. So, I am going to transform the equation once I write down the H total such that everything will just be in the form of pH or H plus and HAC naught, and then I can solve for it, right. So, let us see how that goes about. So, let us see that here we have H total is equal to concentration of HAC at equilibrium plus concentration of H plus at equilibrium minus the concentration of OH minus, right. This is just the balance from here, right, H total. That is going to be equal to, it is going to be 1 times, right, 1 times the HAC naught. And so, what are my unknowns here? This is the unknown variable that I am trying to find out, and these two are interrelated, and this seems like an issue now. HAC, I do not know what the concentration of the protonated form is, right. So, how do I go about it? So, keep in mind that we can try to approximate that by using your ionization fractions, right. So, in this case, what do we have here? HAC is nothing but what is HAC in terms of ionization fractions? Alpha naught into HAC concentration plus AC minus concentration, right. And as you know, if you look at the balance with respect to the acetate, what is that now? Acetate total is equal to HAC plus AC minus, right. And so, I am going to plug this in here. So, the concentration of HAC at equilibrium is going to be equal to alpha naught times AC total. Again, acetate total seems like we do not have the information, but again going back to the relevant drawing board, let us see, right, what do we have? We can again conduct the balance there, and what is the source? Only source of this acetate, I guess, that is from the acetic acid you are initially putting in, or you are trying to put in anyway, right. So, what is that equal to? It is going to be equal to HAC naught, which is again the unknown variable that you are trying to calculate, right. So, that is what we have here. So, that is going to be equal to alpha naught into HAC naught, right. So, this is what we just derived, and I am going to plug this in here, right, or plug this in this variable. So, alpha naught into HAC naught plus H plus, and what is this OH minus, I guess, OH minus, how do we write that? We know that water can dissociate into H plus and OH minus. So, the water dissociation constant Kw is concentration of H plus into OH minus, and again why do not we have H2O here, the variable here, because it is a reactant, right. And why is that? Again, in general the dissociation constants or equilibrium constants are written in the units of activity, and activity of water, right, in this dilute system is going to be equal to 1, right. So, that is the reason we do not have the denominator here. So, anyway, Kw equal to H plus into OH minus. So, OH minus is going to be equal to Kw is 10 power minus 14, I guess, right, by concentration of H plus. So, minus H plus by Kw value is 10 power minus 14, right, and that is equal to my unknown here HAC naught, right. So, alpha naught into HAC naught, which is my unknown variable which I am trying to calculate, H plus by 10 power minus 14, which is Kw equal to HAC naught. So obviously here we have the information with respect to H plus, and why is that? Because I am trying to get to the what do we say now, case where the pH is going to be equal to 3, as in what does that mean? It means activity, or in this case H plus, is going to be equal to what now? pH is equal to minus log concentration of H plus. So H plus is going to be equal to 10 power minus 3 molar units, or molar, let us say I am going to approximate with molar units now, right. H plus is going to be equal to 10 power minus 3 molar units. So I can plug this in, but looks like I still have an issue with alpha naught now. How do I calculate alpha naught though? Let us move on to the, okay, next slide. Let me, so it is alpha naught into H AC naught plus H plus minus H plus by 10 power minus 14 is equal to your H AC naught, and you already have the information that H plus is going to be equal to 10 power minus 3 molar. And why is that? Because you know that the solution that you want, because you know that at equilibrium you know that the pH you want is pH 3. So from that we have the concentration of H plus. So right, that is the whole key here. These are the inverse dose problems, I guess, right. So here we are going to plug in those values, but the issue is that we need to be able to calculate alpha naught. But what is alpha naught though, right? It is going to be a function of pH or H plus and pKa or Ka, and we know the formula for this. It should be relatively apparent by now. So HAC is a monoprotic acid, right. So you have two ionization fractions, alpha naught and alpha 1, and we know that alpha naught is equal to concentration of H plus by concentration of H plus plus Ka. So alpha naught is again H plus by concentration of H plus plus Ka1, right. So you have the numerator H plus you know, and Ka1, because you know pKa of your acetic acid is what now, 4.7, that is equal to minus log Ka. So therefore Ka is going to be equal to 10 to the power of minus 4.7. So alpha naught is a known value, HAC naught is what you are trying to calculate, H plus is a known value, H plus is known, and so here now we are just left with an equation, one equation and one variable, right, and thus you can calculate your HAC naught. So what is HAC naught again? In this case it is the concentration of the acetic acid that you need to add initially to your solution, right, the relevant total concentration, such that you will end up with a pH of 3. So you can solve for that, which we are not going to do now, but let us try to see how to do this by VMINTEQ though. So that is something we need to look at for a second, right. So let me erase this. So that is a bit of not an issue though. So here we are going to go by trial and error, right. We can set up the relevant what do we say component balances, but here how do I go about that? It has no way of back calculating it, right. So what can I do though? I am going to say that I am going to change my acetate total and H total until I come up with a pH of 3, right. So that is what we are going to do here. And what is my HAC total? Let us say, let us go with that, and here I am going to edit the list directly because we use this. Okay, so let us say HAC, where do I go here please? So H total and acetate total are going to be the same concentrations, right, that is going to be your HAC naught. So that is going to be, let us say for the sake of my ease, I am going to use 1.6 millimolar again, right, and key here back to main menu, pardon me, I think I made an error here, 1.6. So going back to the main menu, so everything else I am going to run the MINTEQ, and so I have a pH of only 3.7 or 3.8. So right, again what are we trying to do here? I am trying to use VMINTEQ by trial and error to be able to calculate my pH, right. So I want to estimate by trial and error how much HAC should I dump initially to be able to go to a value of pH 3. So in general, from intuition you should know that the pH in this case is much less than the pKa value, right? pH is less than the pKa value. pKa is 4.7, the pH I am trying to go to is 3, right? So what does that mean now? At pH 3, most of the acid that you going to put in is going to stay as the protonated form, right? So what does that in effect mean? That you need to add a lot of acid, right, to be able to come up to your particular pH. So that's what we are trying to look at here. So let's see, our values weren't good enough, so I'll go back to input menu, edit the list, maybe take, where do I edit that here? So again we are going to try to increase the value. Let's say now what do we say, 10 might be a bit high, we are going to see why. And then back to main menu, and let me run the MINTEQ, and hopefully now at least, even now as you see, right, even at 10 millimolar concentration we are unable to get to our value 3.3 only. Why again, why is that? So the issue is that, so here it's concentration, or let's say ionization fraction and pH, and here you have the speciation. So this is HAC and this is AC minus, and you know that the pKa value is 4.7, but the pH you want to go to is, pH is 3. So this is your target, right? So what does that mean though? So it means that, because again I am trying to use graphical representation to help you understand, I guess, right? So as you see here at the graph, at that particular pH you see that almost all of your acetic acid will stay in its protonated form, or HAC, right? So very little is going to be dissociated as AC minus, or dissociated into AC minus, right? So if very little of it dissociates into H plus and AC minus, so there is very little source of your H plus. So very little H plus is actually given out into the solution. So why? So thus what do you need to do? The total, what do we say, concentration of your acid needs to be very high to be able to achieve that pH. Why is that again? Because the pH is less than your pKa. Again let's go back to VMINTEQ and check that, I guess. So back to input menu and edit list here. So it's logarithmic scale, right? I am going to run the MINTEQ now, and now I see that it's relatively reaching pH 3, but not yet. So we'll go with one more trial here. So I'm going to go back to the input menu, edit the list. So maybe again go to 100, let's say. So I'm going to increase it further. I probably do not need to increase it by this value, but because it's logarithmic scale, I'm just trying to be on the safer side. And back to main menu, and I'm going to run it. So now I guess it's below what do we say, pH 3. So again one last trial before we stop this iteration, let's see, not iteration, pardon me, this trial and error. So I'm going to go with 60 now, but that might be a bit tad less. So again as you see, when you are trying to back calculate, it's easier to do it by hand though. Anyway, 2.993, so that's close enough. So you need to add a lot of acid in this case. What is it now? I think 60 millimolar, right? So that's considerable amount of your acid to be able to reach pH 3, right? So in that case, let's say a question would be, let's say, or a better question could be, so which acid would you choose if you want to get or use a minimum amount of acid to be able to come up with pH 3? So let's just discuss that for a second, please. So the question is, we saw that HAC naught was what now, had to be almost 60 millimolar, right, to be able to come to or get the solution pH down to pH 3. And why is that? We just looked at that particular case here. So the other question that we are going to have a look at is, so which particular acid would you choose, right, so that you can use a minimum quantity of your acid so that you end up at pH 3. So which one would you choose now, right? So obviously the key is that with your background you will try to choose a acid whose pKa, right, is less than the pH that you are looking at. So pH we are looking at is 3. So you want to choose a pKa less than pH 3. So why is that? So when the pH is greater than pKa, what does that mean now? It means that the acid, whatever it is that you add, most of it will be in the deprotonated form. What does that mean? In effect mean, it means that the H plus is going to be donated, right? So when H plus is donated, then the pH can drop out, right, or not drop out, pardon me, it can drop or decrease. So that's the reason you want to choose an acid whose pKa is less than the pH under question. And so you can choose various acids. So I guess HCl, H2SO4 or HNO3, these are all strong acids with whose pKa is going to be less than 3, right. So when you choose these acids, it's probably going to be such that you are going to end up with using minute concentrations to be able to come up with your particular to come up to pH 3. So again, let's do that again on VMINTEQ. So now we are going to look at HCl. So let's see how much HCl do I need to add to be able to come up to pH 3, right. So we are going to try that out. So I'm going to go back to Excel and input menu. So I'm going to edit the list, right. So delete this estate, back to main menu. I don't need organic compounds now, and Cl, where is Cl here? Okay. And add to list, I'm going to edit it here. Okay, 60 millimolar, I guess, right. Again, why are H total and Cl total the same? So we don't need to again go back to our particular iteration. It's because they are the source of H total and Cl total is only HCl, right. So we are going to move on with that, right. So back to main menu. So for the first run, I'm just trying to, as for a check, let's say, trying to use the same concentration of acetic acid that we used earlier to get to pH 3. So let's see with this case what's the pH going to be. As you see, the pH is much lower, 1.3. So at the same levels of acetic acid that were added earlier, which was 60 millimolar. So earlier it went to pH 3, now it dropped down to 1.3. Well, it might not seem like a huge drop to you, but keep in mind that pH is negative logarithm of H plus. So what we are looking at a logarithmic scale, right. So that means each change in unit of pH means there is a 10 times a change in H plus, right. So it's a magnitude of 1, right. So again, so it's almost 100 times lower. The H plus concentration is 100 times higher, pardon me. So we don't need that. So let's look at again input menu, edit the list. So let me go with maybe 1, 60 times less, let's say, and we are going to go with 1, go back to main menu and run VMINTEQ. And so now you see that the pH is 3.016, right. And what's the explanation here? Because the pKa of your particular HCl, right, it's probably near 0 or less than 0 probably. It's more or less going to dissociate, not more or less, everything is going to dissociate at around pH 3. So while you had to add 60 millimolar of your particular acetic acid, only 1 millimolar or 60 times less concentration of your acid is going to be good enough to be able to achieve a pH of 3, right. So again, same case, let's try it out with H2SO4 and HNO3. So I'm going to go back to the main menu here, and I'm going to edit the list. It's not going to be Cl minus anymore. Back to menu H2SO4, right. Okay, so this is one thing we need to look at here. So now let's say I'm adding H2SO4 though. How is it going to change, right? So earlier we added HCl or HAC, right. They were all, or they were both monoprotic acids, right, only one proton. But the key here is that H2SO4, it can give out how many now? 2 protons. So how will this particular speciation change? Let's look at that. So we have what are the species going to be in this case? H2SO4, HSO4 minus, SO4 2 minus, and H plus and OH minus, and choosing H plus and SO4 2 minus as my components. These are the species, these are the components I am choosing. So if I am just doing it on H plus rather than, and not getting that done on SO4 2 minus, so H2SO4, HSO4 minus, SO4 2 minus, H plus and OH minus, and my source is the initial H2SO4 that I am adding to the solution, right. So here it's going to be how many H do you need to form H2SO4? You need 2. How many H do you need to add to form HSO4? 1, 0, 1 and -1. So the key here is that H total is going to be twice the concentration of your particular H2SO4. That is the reason we just looked at this component balance, right. So H total is going to be 2 times the initial concentration of your H2SO4 initial. But what about SO4 though? It is only going to be 1 because you only need. So for example, let's just for H2SO4 let me write down the formation equation, right. How do I form that? I need 2H plus 1 SO4 2 minus, right. So that is where we are getting it from. So SO4 total is going to be 1 times H2SO4 naught, right. So again this is the key here. So let us try to go back to our trial and error. So we are again trying to look at how much H2SO4 needs to be added if I want to achieve a pH of 3, and we are going by trial and error. The reason we looked at the component balance just now was, unlike the case of HCl or HAC, right, the H total and Cl total are not going to be were similar earlier, but this time though H total and SO4 total are not going to be the same. Why is that? Because H2SO4 is a diprotic acid, right. So it can give out 2 protons, and that is what we just looked at. So H total is going to be twice that of SO4 total. So let us look at that, I guess, and we have H. So if H total is 1 millimole, what does SO4 total need to be? Where is SO4 here, please? Well, I guess this is SO4 unless any other cases. Right, that is SO4. Where is that again? I think I missed that again. This is the oxidation state, sulfur in oxidation state 4, 0 and -2, S as sulfur, I mean sulfate, pardon me, and we just mentioned that it needs to be half of what it is with respect to your H total. And what does that mean? That means it is going to be equal to 0.5, right, and that is add to the list. Let us check that as 0.5, right. And I am going to go back to the main menu and run VMINTEQ, and I see that now again the balance comes out to be right. So the pH is again around 3.035. So how much acid do I need to put in if it is H2SO4? I only need to put in 0.5 millimole, right. So how do I know that? Coming back to the input menu and edit list, so it is equal to the SO4 total, right. H total was equal to twice the initial acid, and SO4 total is equal to 1 times the initial acid, right. So that is why the acid that you need to put in initially is going to be just SO4 total, which is why it needs just to be 0.5 millimolar. So let us compare what we looked at until now. So to get to pH 3, how much HAC did we need to add, and how much HCl, and how much H2SO4? HAC we had to put in 60 millimolar, right, and that is what we looked at earlier, approximately pH 3. For HCl it was around 1 millimole, right, and for H2SO4 it is 0.5 millimole. And what is the reason? I guess the pKa for HAC is around 4.7, but for pKa of these 2 particular acids of HCl and H2SO4 is far lesser than 3. I believe it is around 0 though, right. So that is the reason why you see a considerable difference in the amount of acid required to be able to come up to your particular required pH. And again we further see we only need half the concentration of H2SO4 when compared to HCl to be able to get to pH 3. Why is that? Because H2SO4 is a diprotic acid and it can give out 2 protons. So looks like the pKa1 and pKa2 of your H2SO4 are much lesser than your pH, which is 3, right. So again what we look at here today, we looked at the relevant, we first try to look at calculating the amount of acid required to be able to achieve a certain pH. So these are the inverse dose or dose problems, right. So how much acid do I need to put in to get to my particular pH? So rather than doing a trial and error in the lab, you can just plug it in, right. And then the second case we looked at is we wanted to compare the relative strengths and weaknesses, or not weaknesses, pardon me, relative strength or or relative strength of a particular acid. So in this case, we looked at 3 acids: acetic acid, hydrochloric acid, and sulfuric acid, right? So we looked at HAC, HCl, and H2SO4, and we saw that because the pKa of HAC is relatively high, which means it's a weak acid, that is the reason why we had to put in almost 60 times higher, right? We put in 60 times higher concentration of your particular acetic acid. But with hydrochloric acid and sulfuric acid, we just put in 1 millimolar and 0.5 millimolar because their pKa value is much less than what it is that you wanted. And here we see the reason why we call these 2 acids as being strong acids, right? Again, this is the take home message. We just need to look at the component balance, plug them in, and get your solutions. And I guess with that, I'll end today's lecture session, and thank you.